Alright, so we're going to get into the next video here, and when I do screen capture, I apologize. For some reason the microphone's really weird till it tunes into my voice. Like it's really trying to pick up something, and so it makes a horrible static sound. So hopefully I talked really early in this one. Maybe I cut it off. I doubt it, but we'll see. So in the last video we talked all about the levels of protein structure, and in this one we're gonna, this is some high level stuff, and so I'll make sure to kind of frame the strike zone on these ideas at the end of this video. If you're feeling a little bit lost, just hang in there, go along for the ride, take it to the end, make sure you understand what I expect you to know, and then go back and just make sure those things are clicking. Because I talk about a lot of stuff here. I was really into proteins once upon a time. I still think they're fascinating. Like they're a huge piece of the future of chemistry, in my opinion. If we ever reach a point where we can make designer proteins to just help mediate whatever chemical reaction we want, the ability to synthesize any type of pharmaceutical or plastic or whatever is going to be forever changed. The ceiling of what we can do is going to be raised exponentially. So that said, I don't know how close we are to that. We were nowhere near it 10 years ago, but 10 years is a long time in this business, so maybe that started to change. Anyway, so we're going to build on those ideas of protein structure, and so we're going to talk about protein activity, we're going to talk about denaturation, and we're going to talk about how, I talked a little bit in the last video on how a protein stays together, but now we're going to really dial it in and talk about how its role in the cell and what environment it's supposed to be in the cell is going to help hold it together, what types of interactions are going to be beneficial to that. And to start out with that idea, we're going to look at this image right here that I so callously skipped over in the last video. So what we have here is a transmembrane protein. So this could be something like, oh man, now I blank on the word when I've got the microphone in front of me. Okay. Anyway, so we've got a protein here, a transport protein. There we go. Okay, we got a transport protein. I know you're thinking you forgot the word transport. It happens to the best, and in this case, borderline worst of us. So don't worry about it. And so we have a region outside the cell. How do you know it's outside the cell? Well, it's labeled exterior of the cell. So you know it's outside the cell. How do you know it's inside the cell? It's labeled interior of the cell. So this is intracellular, this is extracellular. So what we are dealing with here is a protein that is both embedded in the membrane, and this is the cell membrane, and it has a piece that sticks into the cell and it has a piece that sticks outside the cell. This could be a signal protein or any number of things. Like this isn't all that uncommon. Some proteins are freely floating around inside the cell. Some of them are actually completely embedded in the membrane as well. That can happen. And then there's like this one that has, it goes across the membrane. And so the cell membrane has a non-polar region in the middle here. So these are long carbon and hydrogen tails. These are long carbon chains that just have hydrogens on them. And then we have a polar head. It's a phosphorus with maybe some other stuff attached to it to make it even more polar. So these little guys here, it's like they have two legs and a head. The head is attracted to water. The tails are attracted to other tails. So just like dissolves like, well, common attractive forces are attracted to each other. So we have a bunch of dispersion forces in the middle here. We have a bunch of non-polar interactions. And on the outside, we have a bunch of polar interactions with water, which is both inside and outside the cell. Remember, we are just fancy water balloons. And so we have polar interactions that are favorable. And so that creates this what we call a lipid bilayer. And that's what a cell is made out of. That is the barrier. What makes this water different than this water? There's a wall separating them. That's it. There's nothing special about the water inside the cell other than that. So there's a controlled region where all the cellular processes can be performed. And we can have more lipid bilayers as well. We can have more membranes, so organelles can have their own membranes inside of the cell membrane. So we can section off within this sectioned off area. We can rope off even more. We can have like a VIP only area. We call that the nucleus. As well as other organelles are made with a very similar fashion. And the neat thing about this is it's self-assembling. I don't have to organize this lipid bilayer. It will build itself. You put these together, and they are going to do this on their own. So it takes a lot of the work out of building a cell. When the cell has to replicate and maintain itself, you know, this will be fixed. All right, so having kind of set the stage for what we're looking at in terms of environment, let's focus back on this protein. So you have a helix here that is embedded solidly in the membrane. And then you have kind of these ribbon regions inside and outside. And so you have two very different environments, types of environments. You have a polar region up here and down here, and you have a non-polar region here. And so it's not just interactions among amino acids in the chain that help hold a protein together, but in fact interactions with their environment that really helps hold them together. And so when we look at this green section here in the middle of this membrane, this is a non-polar environment. And so that means that we're going to want favorable interactions with that environment. Otherwise, it's just going to shoot out. It's just going to go to the polar area. If it wants to be surrounded by polar stuff, it could slide up or down and be surrounded by polar stuff. So to be anchored to the membrane, we would expect to see side chains that are hydrophobic, just like the lipid bilayer is. And when we look at these ribbons, we would expect things to be hydrophilic. And that could mean polar. It could also mean that they have ionized acid-base side chains. And so when we look at our breakdown here, we look at this intracellular region. So at the bottom, it has, we've got about what? We've got 39 total amino acids here. And 12 of them are polar and 11 of them are acidic or basic. So 23, so about almost 2/3 are really going to favor water interactions. There is some nonpolar stuff, but look what happens when we get to this section. There's only 19 amino acids and 17 of them are nonpolar. There's almost no polar amino acids in here. And then we get up here, and it's about 2/3 again that are polar. So we have a lot more polar side chains, a lot more favorable interactions with the water around this section, just like we had down here. And then we have a lot of favorable non-polar interactions with the environment in the middle. And so that's going to keep this protein solidly anchored, because these side chains aren't going to want to interact with the water down here. They're not going to want to interact with the water up here because those are polar environments. So they are, you know, they're snug as a bug. They're happy right where they are. That's going to keep this protein anchored and oriented where it needs to be. And that's going to be, in all likelihood, essential to the function of this protein. So it needs to be there. So this is an anchored protein. Now, if you have, I'm going to throw in a hypothetical here, so hang on. So we're not talking about this one anymore. But if you have a protein that just hangs out in the intracellular region, what you'll see is that polar and ionic side chains, basically hydrophilic side chains, are going to orient to the outside. They're going to orient and interact with water. They like the water. They're going to interact with water. And hydrophobic side chains are going to tuck away in the middle. And so that interaction with water is going to kind of help keep that protein pressed together and hold its shape, because the middle isn't going to want to expose itself. It's not going to turn itself inside out because of these attractive forces, these interactions. And so I cannot stress this enough. Form and function are intrinsically related for proteins. If you lose shape, if you lose form, in all likelihood, barring some sort of miracle, you are going to lose function as well. And so all these tricks that proteins are using to be sticking together, that's going to help them keep their function. That's going to help keep what we call protein activity. And so there are a couple ways you can lose function. So now we're going to talk about denaturation. So when a protein is denatured, it has had a change in shape that has disabled its function. And there's a couple ways to do this. So if it's folded together correctly, it's active, it has what we call protein activity. Yeah, I know, it's a little repetitive, but it's doing its job. It has function. If it gets crumpled a little bit, and it's not able to do its job anymore, it's denatured. It's still folded, but it's not folded correctly. Or you can denature it all the way back to a noodle. You can take all the folding out of it. That's like as denatured as you can get. But essentially it's denatured. It's as unfolded as you can get, and it is also denatured, I should say that. So it's definitely not going to do its job because it's just being a long chain of amino acids now. And so there's some tricks that proteins can do. So a very common type of protein is called an enzyme, and so this is going to assist a chemical reaction, or we say catalyze a chemical reaction. And so substrates is just a fancy way of saying reactants. And an active site is where these reactants are going to pop in, and then the enzyme is going to help guide the reaction. It's going to make the reaction happen much, much, much easier. A lot of the reactions that are done in our bodies would not be spontaneous at body temperature without the help of enzymes. Like, we would not be able to do them. Like, the two chemicals, the two molecules could bump into each other all day, and they wouldn't collide hard enough for a reaction to happen. They wouldn't be hot enough. But with an enzyme kind of helping, guiding, and it's like the difference between using a machine press and just throwing something at something else and hoping they stick together. Like, this is the machine press. It's going to put pressure on these reactants. It's going to help hold them the right way, and then boom, we're going to form products. A reaction is going to happen, and then it's going to release products. So that's what an enzyme does. And so it has to have the right shape to do this. It's like a lock and key. The substrates are the key, and the protein, the enzyme, is the lock. And so if the lock gets bent out of shape, the key doesn't fit anymore, it can't assist the reaction. It's no longer active. And again, it could be a slight change in shape, it could be completely back to a noodle, but either way, it wouldn't be able to do this anymore. It wouldn't be able to catalyze that reaction. And let's see, we got a really specific example. Not going to worry about that. And here's an even better, look at that. Like, got an energy diagram. Oh, we'll talk about those later. So we're not going to worry about that right now. Oh yeah, and so I talked about how phosphorylation can be used to turn proteins on and off. Another neat trick is a lot of times ions can do the same thing. So zinc is often used to activate or deactivate enzymes. And so this is an enzyme that when zinc is bonded to one site, the active site comes alive and it starts performing its job. When you no longer need the protein to be doing its job, the zinc pops off and it's just sitting there. It's like it's idling. It's not working anymore. But by just adding a zinc, it'll come back on. And that's a lot easier than just always breaking down and rebuilding the protein as needed. Calcium ions are another common one for this trick. And there's a few others from time to time. So, I guess that's it for kind of the new ideas. So let me I like to say frame the strike zone, because I just threw a whole bunch of wild pitches at you. Like, what's going over the plate here? Like, what do I expect? So, it's been a wild and crazy ride through proteins. Thanks for hanging in there. So you should know what primary, secondary, tertiary, and quaternary structure are. You should know how to determine what level of structure you're looking at based on an image. And so with primary, it would just be a list of letters, essentially. Or maybe it shows you a noodle, anything like that. That's primary structure. Secondary structure, you wouldn't even see the whole thing. Look at this. Like, you look at this. There's a alpha helix. There's an alpha helix. Looks like there's two in here. There's a beta pleated sheet. So those are all secondary structures. And then when you know how they all lie with respect to each other in 3D space, as well as any other parts of the chain, you have tertiary structure. Now this protein we're looking at here, carbonic anhydrase, does not have a quaternary structure. And let me ask you, before I answer this question, why does it not have a quaternary structure? Okay, so hopefully you remembered quaternary structure only occurs if multiple peptide chains are needed. This is a single peptide chain protein, and so it only has tertiary structure. There's no need for quaternary because there's not another peptide chain. Now, how would you know? Well, generally what we'll do is we'll just color code blobs. That's the honest truth. You see multiple color-coded blobs, you go, okay, there's multiple peptide chains. I'm dealing with something with quaternary structure. I know it through quaternary structure. That's the level of detail I understand it to. Alright, so all that was kind of out of the first video. You should also know what the N-terminus and the C-terminus are. And what else? Oh, and then side chain properties, how that helps kind of hold the protein together, how the environment the protein is going to be in affects whether you want hydrophilic stuff on the outside or hydrophobic stuff on the outside, or, you know, is it going to be anchored to a membrane because you see a bunch of hydrophilic or hydrophobic side chains, you know, that sort of thing. And the idea of denaturation. So there's actually a couple ways to denature as well. I didn't talk about that, but it's always good to keep in mind. So like, how do you denature a protein, right? How do you knock it out of commission? Well, there's a couple tricks you can pull. You can heat it up. So like eggs are mostly protein. You cook an egg, you see a change. You're actually denaturing the proteins in the egg. They're changing form. They're going from a liquid to a solid when you cook them. So that that's going to cause misfolding, which causes structural change, which is a form of denaturation. Essentially, you're just on an atomic level, you're just shaking that thing to pieces is what you're doing. You can change pH, and so that's going to affect the ion-ion interactions, because if you're not at physiological pH anymore, either your cations or your anions, one of them is going to go away, depending on if you raise the pH more or lower it. And so that's going to affect the structure, because you no longer have those ion pairs holding it together. You're going to lose shape. You're going to lose function, because the pluses are no longer attracted to the minuses. Now you only have pluses or you only have minuses, but you don't have a plus and a minus to stick together. You can change the polarity of the solvent. So say you got a bunch of protein in water, and then you pour it into a nonpolar solvent, something like acetone. Those proteins are going to flip inside out, because they had a hydrophobic inside, they had a hydrophilic outside when they're floating in the water. You throw them in something else, it's going to flip. All the hydrophobic stuff is going to be attracted to each other, but not the environment, because now the environment is hydrophobic. So the hydrophilic stuff, yeah, it's going to fold on the inside, hydrophobic stuff the outside. It's going to turn inside out, which is going to be a significant change in shape. You're going to lose function. And then my favorite, so there's 4. So there's pH change, heat, polarity of solvent, 1, 2, 3. And then there is the best one. This is the one that, and this gets used in labs. So everything I've talked about has caused misfolding. This one will actually take it all the way down to being a chain again. And so when you have to figure out the primary structure, you need to get that protein completely unfolded. And to do that, you denature it with urea. And if you aren't aware, urea is the main ingredient in urine. That's where the name comes from. So that's what makes your urine yellow, is urea, I think, probably. Yeah, sure. Yeah, it's how we get rid of our nitrogen waste. Yeah, the yellow color comes from that. If it's come from anything else, you've taken too many B vitamins. I don't know. There's some other environmental factor at play. And so this isn't totally understood. Like, people still don't quite understand why it takes it all the way back to noodle state. It makes a peptide chain. But they know it interferes with the hydrogen bonds between the protein and the water, and within the protein itself. That's about all they understand. They don't quite get why it takes it all the way back to noodle. But I used to always give this example in class. So, you know, there's, like I said, like, you know, cooking eggs, that causes misfolding. You see the change in the egg. So urea will denature proteins, and then the real life application of that, I used to say jellyfish stings, but then I found out, my heart was broken, that apparently peeing on jellyfish stings doesn't actually help with them. There's one kind that does, that has a protein-based venom or whatever it is they have. toxin that the jellyfish hits you with. But if you ever step on a sea urchin, then urea will help save your life, or at least, you know, stop. I don't know if they're fatal or not. Stop the pain. And so once again, you can run wild on the beaches, saving lives with a full bladder, and you're welcome for that information. And that's real. So my favorite part about that, though, is I'd throw out jellyfish stings, and then I think it was like the second time I taught the class, or the third, a student had looked it up, and the next class came and called me out in front of everybody. It was like, I hope you never peed on anybody that got stung by a jellyfish, because you did nothing but add insult to injury. But it does work for sea urchin stings, according to their research. And then I looked it up, because I was like, what, really? And apparently it's a bit of an urban legend, but there is like the Portuguese man of war, something like that. I'd have to look it up again. There's one type of jellyfish that it does help with. But also in labs, like they really do. They have lab grade urea solutions that they use to denature proteins. Okay, and then in terms of the new stuff, we got a little sidetracked there, but you should understand what denaturation is, protein activity, and that interplay between the environment and the protein. So there's a lot I talked about, and so much just kind of help you out with biology. I always like to give a leg up in this section on that, because you'll probably notice now the classes have really started to dovetail. So early on they talk about some straight biology stuff, I talk straight chemistry, and now we're getting in the area where the ideas are blended. And so you're kind of getting two perspectives. You're getting the best one from me, and then you're getting the other one from your biology instructor. But whatever I can do to kind of help out on that end of things, you know, I have a background in this stuff. I like to lend my voice when I can. And yeah, so we'll leave it there. One thing you can do, there's some really cool simulations that people do. I often show them in class. I felt weird just showing someone else's video and narrating over it, so I'm not doing it in this class. But you can look up, they're called MD, just literally the letters MD, or molecular dynamics simulations of proteins, and you can just watch them jiggle. That's what they do. Proteins just jiggle. They're getting pounded, pushed around by the water around them, and that's what drives a lot of protein activity. It's just random collisions with the water around them. And so we can use computers to simulate those collisions, to simulate those environments, and to make movies of how proteins behave. And so you can look up a ton of them on YouTube. And you know, if you have a moment, I encourage you to. You know, you won't get tested on anything you see there, but it's just kind of fun to see like what's happening on the molecular level being represented on a computer screen. So I encourage you to do that. Alright, so we'll leave it there for the protein section. I won't ramble anymore in this video. Hopefully I did a good job of framing the strike zone for you, because like I said, I did talk about a lot of stuff. But if you have questions, as always, email, use Moodle chat, use the forums on Moodle, whatever it takes, you know. Throw a bottle in the ocean with a note. However you want to ask for help, go for it. I'm happy to provide it once I become aware. But otherwise, try to have a little fun with this section. I think proteins are pretty cool. Hopefully you're starting to feel that way too.